Yeah, I tried to keep it together, but that's somehow a funny article. Swiss Polar Institute. Okay. Erratic reminiscence of glacial history on Disko Island, Greenland. Gerald Raab. For those who don't know, there was once this comedian in Germany. His past name was also Raab, but that might just be a coincidence. Glaciers and ice sheets are observed to rapidly change under the current global climate conditions. This is particularly the case for those in Greenland. For future projections of change and long-term or multi-millennium perspective on changes of Greenland ice sheet drainage and local glaciers are of key importance. For example, the dating of glacial deposits such as moraine and rock boulders provides an essential time component to the understanding of glacial retreat. Our project focuses on glacial erratics. Okay, just to make sure everybody is following. Erratic meaning. Not even or regular in pattern or movement, unpredictable. Geology, a rock or boulder that differs from the surrounding rock and is believed to have been brought from a distance by glacial action. Our project focuses on glacial erratics, rocky material that differs from the rock type in its current resting place. On Disko Island in western Greenland, there granitic rock boulders from the Precambrian basement rest on the Paleogene mafic plateau that constitutes most of Disko Island. Our goal is to identify the time of deposition and the original source of these erratic boulders. We will use petrographic analysis to determine where these erratic boulders originated from. To establish a deposition chronology, we will measure terrestrial cosmogenic isotopes. Studying the southern slope from sea level to 800 meters above sea level along the coast of Disko Island will provide important constraints in the thinning and timing of deglaciation of the former ice stream, which covered Disko Bucht, a large bay between Quetertasuaq and Ilulissat. Yeah, I told you it's going to be funny. In addition, the results will provide a minimum age constraint for adjacent rock glaciers that are being researched by the partnering SPI-funded exploratory grant project Rock Disko. So now, it's not good quality, I know, but you can see dendritical patterns here already. And the old question remains: if these valleys are formed by glaciers, and glaciers are working like nature's bulldozer, where is the pile? No piles anywhere. Not one single pile. Mapping and dating of erratic boulders on the plateau will provide new constraints on ice map and ice sheet thickness during the last and potentially previous ice age glaciations. It is currently not known if the ice sheet flowed over this mountainous plateau in the last ice age or in which previous ice age, and hence dating will provide former ice sheet thickness constraints. So constraint is always a problem. So obviously they went to Greenland to find problems. Based on this background, we headed into the field with a clear assignment to take samples of the erratic boulders that are scattered on the mafic plateau to determine their deposition ages and origins. The fieldwork of our project started with 4 days of travel by air and sea. We finally reached Disko Island In the summer of 2021, unfortunately, we were not welcomed by the best weather. Nevertheless, we took up the challenge to get into a good daily routine as early as possible. And they found a rock. An example of an erratic boulder on our first field day after arriving in Disko Island. So, they're just explaining what they're doing. You can read the whole article here. And here you can see how they took samples out of the rock with a nice hat. Swiss Polar Institute. So, where is the pile? Where are they? Yet another rock. A wonderful example of an erratic boulder roughly 800 meters above sea level. At which point in history was it deposited here? 12,000 years ago. Let me show you something else. This is not to scale, it's really much simplified and there is so many things missing. But if we have this kind of ground discharge events, you can be really sure that we also have all kinds of clouds and winds and all these kind of things. But the thing is, that's now a little bit different picture. But if you could see this from somewhere, if there would be this huge thunderbolt coming down and scatter the whole landscape and all this stuff is going on, there's stones and boulders flying into all directions. They can fly really far. And at the same time, they get electrically altered. So they will be all of a sudden much older, according to common geology, because they don't take the electrical aspect into account. So if you take, for example, I don't know, it's just, I don't have a lab. If I would have tried those things out already. Like, take some stone from the Swiss Jura, for example, which is basically chalk, and then put it in some machine and induce a large amount of electricity and stuff and watch what's coming out. Maybe it's granite, I don't know. And if you repeat the same process again and again and again, it will be every time a different rock afterwards. So the other thing is also what I have been talking about, those glaciers. Let's draw it once again. We have here now a lightning strike, and there is groundwater here somewhere, and the water is attracted, it will go up. It doesn't care about gravity. The electrical force is billion times stronger than whatever gravity. It will rise up. And where it makes the connection to the heavens, the lightning bolt or whatever, and there's like debris getting attracted to the electrostatic field of the whole thing, and it gets warm and things get vitrified and glued together and fused together and all these kind of things. And all what is left is the one water vein which went to the top where it touched the lightning strike. And some of them might be that big that they are continuing until now with producing water. They're pumping up the water still because they are still connected to the groundwater. And there might be even some electromagnetic mechanism to that as well. I don't know. But that's how glacier got formed. And it just pulled out the water and then it froze and it just continues pulling out water. Because underneath the glacier it might be much warmer than on top of it. So there's still water flowing from underneath, which is feeding the glacier and is going downhill. And when the whole thing, the whole process is always at the beginning of a valley. So it's the highest point somehow where the valley is ending. This is where the glacier starts. And since we learned that there's glaciers, they are just like growing into all directions. There might be a dwell underneath. For example, Greenland, if you would watch it without ice, I was making a video about that. How should the ice go over the top if there is no push from below? Yeah, maybe I should send this guy this video. Swiss Polar Institute. Disko Island. 12,000 years ago, all this stuff went down. Yeah, I'll leave it here. Thanks. Bye.